recording activity. And then we want everyone to have a nice time and an opportunity to participate and contribute. So please be kindful and respectful to everyone and everyone's views. Also, be reminded that captions are available via Zoom, and then you can always put questions in the chat. How are we? Okay, so on to introducing CSID. I'm sure we have participants today who are very new to the network. So the CSID network seeks to enable members to collaborate on co-designing and building impactful CSID tools. The network launched last year to enable its members to collaborate on these goals. And we've been doing this since CSID Net was established in 2024 as a way of getting voluntary collaboration among research and practitioners to pursue the unified purpose, of building, designing, and maintaining impactful CSID tools. How are we growing CSID Net? So we have a fellowship program. Our fellows are building either local or regional communities of practice in regions that are usually underrepresented in quote global discussions around CSID. And so by doing this, we are hoping that we'll reverse some of the challenges we have around so-called global issues where people from the global south are, usually not participating in the tools and processes designed to serve them. We also have gatherings, be it virtual or an in-person, because we believe in gathering people around to learn and share among peers. The photo you see there is from our first annual general meeting that was held in July in Thailand, where we brought over 70 people from more than 40 countries to share and co-design the network. And then we also have membership. We are community-led. So our members are not just audience, but they are also active participants in the network. As I said, I'm a member of the training and education committee. I've been contributing together with my colleagues in that committee to making sure that we have this session today and many more exciting sessions planned in the future. Yeah, so this diagram is just a brief overview of the core working groups within the CSID network so far. So we have the fellowship program, we have the committees where members serve on and through which members drive the network. We have also working groups, as you can see, some of them like the ethical framework, model repository, and so on. And then we have the small network staff that also helps with the operations of things within the network. Yeah, and this is an even more picturesque view of our committees so far, the people that sort of like drive the network and the spirit of collaboration and learning, and from each other and so on. Yeah, we have the governance, training, collaboration committees and so on. Yeah, and then Yeah, there will be more events and trainings coming on. Uh, um, and there'll also be applications for co-hosts open sometime soon. As we delivered on these events and trainings, we are still committed to our values of membership, member ownership, mutual aid ethos, and, sustainable collaborations. So yeah, I think this is a quick and brief introduction on my part to the CSID network. And I'll hand over to Daniel to help us move on with today's section. Thank you very much.
Okay, all right. Thank you so much, Sam, for that wonderful introduction of CSID network. I believe some of our participants on the call are now familiar with what CSID network is all about, what we are doing, and a whole lot that you guys will still be learning subsequently. I will be introducing Lisa. So Lisa will be facilitating today's section. She is going to be talking a whole lot about climate. I know that some of you are already saying that you are not familiar with what climate is all about. So she's going to be talking about climate data literacy and responsible use of climate data for CSID modeling. So not to waste much of our time, I think I would have Lisa to just do a proper introduction of herself, get to tell the participants more about what she's doing and a whole lot of that. Thank you so much, Lisa. You can have the floor.
Great. Thank you so much. And thank you for allowing me to run this training. So as you said, I'm a climate scientist. I want to say a climate scientist and a kind of a data manager. So I sit on that kind of more technical side of climate science. I've been part of the CSID net since its inception. And I have to say I'm passionate about how people use climate data. And I want to try and encourage people to use it responsibly. So that's why I put forward this talk. So without let's just move straight on to this. So I don't know if any of you have seen this kind of animation. This is the temperature over time. You can see in the early years, it was relatively kind of, I want to say, cooler. And then once you get into the 80s, you see this ramp up of temperature until the last few years. It's been, we're hitting over 1 degree warmer than the long-term average. And so this is just an animation. You may be wondering why I showed that. And the reason is I just want people to understand that climate change isn't a problem for the future. If you're working with anything that is impacted by climate, this is a problem of the present. So yeah, if you're doing CSID net kind of work, you need to keep in mind that the climate is changing and that's going to have a massive impact on your modeling. Okay. So I mentioned, climate literacy or climate data literacy. What exactly is that? Climate literacy is a much bigger field, but what I'm trying to get at is the ability to understand, interpret, and critically evaluate climate records. That is really, really important. And using this knowledge to identify, what are the variables, what are the trends, and to contextualize this information so that you can do evidence-based decision making. I apologize. I've got quite a lot of content, so if I do rush, I'm sorry. But as I also said in the chat, we have a number of people who I've brought in, thank you guys, who are here to answer questions. So if you have questions. If I don't kind of explain myself well, please just actually put your questions in the chat, and they will field them. Okay. So climate literacy is very linked to responsible use. So responsible use of climate data, specifically for CSID modeling. We want to make sure that what we do is, scientifically sound. We want to do good science, but we also want it to be relevant, relevant to where we're working. So if I'm working in Africa, I want that to be relevant on the ground. We also need to make sure that what we do and the output that we produce is ethical, and that we distribute our data and our kind of workflows and everything we do, that we distribute it equitably so that those that are most affected are benefiting from this research. And that's very much linked to transparency and reproducibility. The FAIR principles. We really want to be able to make sure that others can follow what we've done and do the same, and build up a body of knowledge. I think what's really nice about this community is there's a strong respect for local expertise. This is very much Global South driven. And I think that is really critical because most of these diseases are in the Global South. And then finally, also, we need to make sure that what we do is, abides by strong data governance, and, we respect the sovereignty of the countries and institutions that supply data for this modeling. So that's very broad kind of scale of where this kind of talk fits in. Right. So just before I dive in, I wasn't sure how much knowledge people had about climate. So I thought I would do some real basics. Okay, so your climate is determined, the spatial distribution of climates across the world are determined primarily by your latitude. If you're at the equator versus at the poles, the amount of sunlight you're getting in is going to be different, and your climates are different. Another aspect is your altitude. The higher you go up, generally the colder it gets. So locations which are, at altitude or in complex topography are generally colder and have kind of quite a lot of nuance, microclimates. The oceans also impact the climate very strongly. So the proximity, how close you are to the ocean, will also modulate your climate. Generally, if you're on the coast, you have a more kind of modulated climate. And if you go inland, for instance, your temperatures are going to be far more extreme. And there's a feedback. So the rainfall and the temperature impacts your land cover. You're going to have forests or grasslands or tundra. But that also impacts your climate. So land cover also is important. Apologies. Almost all of my plots are going to be about temperature, and they're going to focus in on Africa or Southern Africa, just because that's where I am. So you can see this in these plots. So the two on the right-hand side is, the top one is rainfall, bottom one is temperature. And if you just, for instance, look at the temperature one at the bottom, you can see South Africa is quite a bit cooler than the rest of the subcontinent. Yes, this is because we're further south, we're closer to the poles, but also if you look at the topography map on the left-hand side, you'll see that a large part of South Africa is actually at altitude, and so our temperatures are cooler. You'll also see that a large part of South Africa is quite arid compared to further, towards the equator. Okay, so the climate is chaotic, but there are some modes of variability that you can kind of determine from, I want to say, within the noise, there are some periodicities. The obvious one is the daily cycle. Every day the sun rises, the temperatures increase, the sun sets, the temperatures decrease. It's like a click. It's there all the time. Obviously, if you're on the equator, your day night is, 12 hours, 12 hours. If you, further north-south, you're going to have differences depending on the season. You also have subseasonal, but then another really, really important mode of variability is your seasonal. So the variation that you see because of, your season going, once around the sun. So for most of the modeling or the CSID community, this is probably going to be your strongest, most important mode of variability. You'll see, for instance, in malaria, you'll see in many places there's a really strong season. And so if you're modeling, you need to make sure that you're capturing that seasonality. You have other modes of variability, for instance, interannual variability. This is primarily driven by sea surface temperatures, differences in sea surface temperatures through time. So you might be aware of El Nino, La Nina, or the kind of INSO. So these are changes from year to year. And then you have multi-decadal variability, and then you might also have some long-term trends. So just focusing in on the graph, the top graph, the black line this just happens to be a time series of temperature. What you can see is, eyeballing it, you can see there's a trend. And so that's the red line. If you remove that trend, you're left with two things. You're left with interannual variability and decadal variability. So you can decompose your time series into these different components. Right. So if I ask you, in the work you've done, if you're using climate data, or if you haven't used climate data, what climate data do you think you will need? I can almost guarantee that you're going to say rainfall and temperature, and some of you might also say humidity. And yes, those are going to be your primary variables. But maybe it isn't just that. Maybe actually you might want to look at kind of some compound or derived variables. It's not just the rainfall. You want to know the rainfall minus the evaporation. Or maybe you're really interested in heat spells and not just the average temperature. Some people are really trying to understand the impact of extreme events. So heat waves, floods, tropical cyclones. Other people may be looking at what is the impact of drought on disease. And there's some kind of, we call them like gradual onset events. They're longer term. They're harder to classify. So droughts and stream flow data, they have a memory. And then there's another example, which is kind of data that tells a story and changes minds. So these are memorable events. So I'm from Cape Town, and so we call it the day zero drought. Basically, the city of Cape Town almost ran out of water. They almost had to turn off the water. And that was an incredibly memorable event for all of us. And it's changed the way people view water. People now value water. You don't see people behaving as if, before, you see them conserving water. You see that it's actually changed how the city works. In another example is the tropical cyclone. I can never remember how to say it. Idea, I can't remember, that came through Mozambique. That had massive consequences. And it's a touchstone. There's a lot of lessons that have been learned from that tropical cyclone. Okay, so if I ask you, if you're going to be running your model, over what period will you train your model? Are you going to grab the last 5 years of records, meaning temperature records, rainfall records, or maybe you want to have a longer time period, or maybe you're really interested in training it during the period of kind of before climate change? Probably not. But then what is your target time period? Are you trying to evaluate or kind of produce output to help you look at the next month or the next season, the next 5 to 10 years, planning for the future? So just when you're thinking about what you're going to be using climate data for, think about those questions. Also, what resolution or your health data or whatever other data you're using, what spatial resolution is it at? Is it regional, national? Is it local city? Or are you actually, do you have data at points? And then finally, what kind of climate data are you really wanting? Are you wanting time series, daily, monthly time series of rainfall and temperature? Or are you wanting just to understand the basics, kind of the spatial pattern? Do you just want the climatologies? Or do you want to know how different things are? So anomalies. Or again, like, are you wanting to focus in on events? Okay. This, I might not dwell on this, but this comes from a really, really useful report that was done by Welcome. And after the session, I will put together a list of resources. So you'll have the websites for some of the resources that I'm kind of highlighting. And so what they did was, yes, you've got these different timescales for climate variables, but what does that mean for your health data, or what, your study? If you're wanting to look at weather events, how much data, health data, do I need to have in order to build those relationships? What if I'm looking at, multi-decadal changes? So what's going to happen, or what has happened over the last 30 years? Then, you'll need to have kind of much longer health records to be able to make that association. Okay, so next section. I often get asked this. So what is the best data set and where do I get it from? Um, so yeah, we're very fortunate to have many different climate data sets out there. It's wonderful to be able to go and say, yes, we have data available. But people don't always understand that the data isn't all reproducing the same or representing the same thing. You get different types of climate data. The obvious type of kind of climate data that I think most people are familiar with is weather station observations. So this is just an image of a automated weather station. They're great. They can give you data on a whole lot of variables, so rainfall, temperature, humidity, solar radiation, all sorts of things, and you can get it at 5-minute intervals. And it really gives you a ground truthing. It tells you what the weather is like at that point. Unfortunately, they're pretty expensive if you're going to put a weather station in. It's also pretty expensive if you want to access other people's weather station data. The Met services generally charge people to gain access to that data. Another issue is, so looking at the map on the right-hand side, this is a map showing where the weather stations are that went into this. This happens to be a global data set called GHCN. So what the colors show you is, the purples to greens are, this is when the record ended. So these are all weather station records. But if you look over South Africa, most of them are kind of green. And that means that those stations closed before or up to kind of 2000, the year 2000. The yellow ones are the ones that are still currently operational. And so what you can see is, for instance, South Africa had a lot of weather stations and they were relatively long records. This happens to be rainfall, long records. But these were all manual stations and they all got closed down and they got replaced by a much sparser network of automatic weather stations. Still, South Africa is pretty good. If you look up at Angola, you can see there's 6 weather stations, 2 of which are still operational, and they're on the coast. And Angola has a very big mountainous area in the center. So that whole mountainous area is not getting captured. The climate of that area is not getting captured. So we have nothing to ground truth. There's no data to be, that gets used in those locations. Okay. So weather stations give you point measurements, but most people want to know what the climate or the weather is like at locations that aren't at weather stations. So you get a bunch of different gridded products. So basically you have your data, your say temperature data for the locations where you have the weather stations, and then they use interpolation or other methodologies to transform that into a gridded product. What's great about this is, generally speaking, it's going to be spatially and temporally continuous. There's data everywhere, but it's generally going to be coarse spatial resolution and coarse temporal resolution. But it's generally free and it's generally relatively available or easy to use. You also get satellite data. So weather satellites kind of started coming in from the 1980s, but there's been a ramp up of different satellite products in the more recent period. This is fantastic because they can look down on the world, and so you can get data for places where you don't have weather stations. So great. Angola, you still do have some kind of idea of what's going on because you've got satellites that go over that area. Some of the newer, we call them what do you call it? Polar orbiting satellites. So they literally kind of wind themselves around the world. They have a kind of an orbit that goes around and around and around. So they have like a small swath that they look down at and they get data for. So you can have really fine resolutions. So some of them are like 1 meter resolution. The problem is there's always a trade-off. They only go over that one location once every few days. So you're only getting data once every few days, and it's always at the same time of day. It might be 10 o'clock in the morning. Also, because they are relatively new, you don't get these long records. You're going to be working with a much shorter record. And then finally, it's important to know that this isn't the same as climate data. It's not at observations. The variables that you can get, or the data you get out of it, it's derived. You need to understand that the strengths and the weaknesses, what it can and can't represent. So yes, it gives you high resolution, but do some research on what the data is actually representing. And then finally, you get something called a reanalysis. Well, you get something called reanalysis products. So you get weather forecast models, the kind of models that tell you if it's going to rain tomorrow or not. Those weather forecast models, and these are actually pretty skillful, and these are global. And so what they've done is they've rerun these models, and these models are, I want to say, they understand the physics of the climate. And so what they do is they rerun these models, reanalyze, over the historic period. So for instance, 1940 onwards. But they kind of use observations to help contain it and keep it, I want to say, keep it in line. When I say observations, yes, it's weather stations, but it's other things too. It's satellite data, it's aeroplanes, it's balloon ascents, it's ship tracks, it's buoys in the ocean. There's a whole lot of data that goes into, kind of gets associated with the model, and then it produces, this is assimilated, and it produces a best guess of what the climate and the atmosphere is doing. So because it's a model, it actually allows you to know what's going on at the surface for a range of different variables, but also up into the atmosphere. So you can look at like upper level winds, or what is the solar radiation, as well as looking at, the air temperature at the surface. So if any of you have heard of the data set called ERA 5, that is a reanalysis product. Okay. But again, there is no such thing as the best data set. So when you are looking at data sets, just always remember that a data set is developed for a specific reason and for a specific task. Well, for example, there's this data set. I love it. It's called the BEST. It's Berkeley Earth Surface Temperature. But I love the fact that they got that acronym. This data set was developed firstly to look at climate change, to look at how the climate is changing over time. Secondly, they wanted to make a data set that was distinct, kind of not associated with the other data sets that were already currently available. They wanted to have something that was so that you can compare. They also wanted to use as many data sets, observations as they could to develop this model. So they're really good at the long-term climate change, but they're very coarse. And this data set isn't going to be useful if you're wanting to look at day-to-day variability or kind of fine spatial resolution. There's always that trade-off. But sometimes people get so kind of fixated on, I want to get the best data, that they forget actually what is going to be good enough for my application. If my health data is at district level, if I only have monthly average district level data, is there any reason to go to higher resolution or want to get a high resolution, high spatial temporal resolution climate data? Also, sometimes, some of the data is far more complex. Maybe you actually just need a simple data set. I threw this one in. Sometimes you need to be careful. Some sites say that their data is the best thing. It is the highest resolution. You should use our data. Generally, it's going to be too good to be true. So just be careful when you're looking at the data. If it looks too good to be true, it probably is. And then this is something that I want to encourage. Why choose? Why try and get the best data? In many ways, I would prefer people to use multiple data sets, climate data sets. Use them as inputs into your model and evaluate the output. How sensitive is your model to the data, different data sets? Maybe it doesn't matter, or maybe it really, really matters. And then you need to go in and really see if you can ground truth the different data sets to kind of select which one is the most appropriate. Okay, so where do you get data from? Climate data from? So originally, the go-to place was your Met Service, or maybe you actually gather your own climate data yourself. But more and more often, people are getting data from either regional climate centers or international organizations. And sometimes you actually do have data sets, for instance, like Weather Underground, etc. So citizen science. And I think give it a year or two, we're also going to have a lot of AI generated products coming online. So yeah, you can get climate data from many sources, and sometimes the same data can be available through different platforms. Okay, so this is just an example. This is a table coming from, it's called the Climate Data Guide. And this just shows you that this happens to be a bunch of different temperature data sets, and this is not the full list. So you have multiple data sets. Each one has different time resolution, different spatial resolution. Some of them have different data formats, and they cover different time periods. So it can be incredibly overwhelming to a user. What data sets do I choose? So this is just a kind of a little bit of analysis I did. So on the top, so the spatial plots just happen to be kind of focused on, I want to say South Africa with Joburg in the center. And so I grabbed a bunch of different temperature data sets out there, and I plotted the long-term average. This is average temperature. And so maybe you go, oh, that one, Cherts, that looks good. It's got the highest resolution. Great, let's use that. And actually, if you look at I plotted the seasonal cycle for each of the the long-term seasonal cycle for each of the data sets. Cherts happens to be the orange one. And hey, you can see there's biases, the different models. But the orange one's kind of slap in the middle. So let's use that one. But unfortunately, this Cherts data set was a research product. It's not operationalized. So you actually it only produced data for a time period 1981 to 2016. So sometimes, depending on what you need, you actually may have to select data using kind of less, I want to say, more practical reasons. Maybe you need to have data that is updated regularly, in which case you're probably going to have, or maybe you need data that's hourly. And that cuts down the number of different data sets that are available because there are very few data sets that actually, produce hourly data up to the present. Okay. That was a bit of a whirlwind. But I think what I'm trying to get you guys to understand that there is uncertainty in climate data. Yes, there's uncertainty in other data sets you're using, and maybe the uncertainty is more. But please don't just think you can grab climate data and just use as is. We need to understand how to incorporate this uncertainty and observations into the modeling work you do. And I think in many parts of the world, pretty much most of Africa, it's probably good to think of all these data sets as just being proxies. We don't have the truth. We don't actually have enough observations to ground truth any of these products. If you're in Europe, you can probably evaluate the different data sets because they've got a very high spatial net, very dense spatial, very dense station network. So you can evaluate. But over large parts of Africa, and I'm assuming South America and other places, we don't have that observational record. So you can't actually know what is truth. Right. This is where I suggested a break. I don't know. Do others want to take the break now? Or should we continue and take a break a little bit later? I'm going to throw that out to the hosts. What would you prefer? Should I continue?
Lisa, I think we have around 15 minutes to the hour, so maybe you can continue with your presentation and we come back for the practical session. Does that sound right?
That's good with me. I
Yeah,
seem to have flown through that a little bit faster than I was expecting. So give me a second.
I see. That's all right. I see emojis saying clapping, and I see comments in the chat saying, please continue. So
Okay, we'll continue.
yeah.
Okay, so that was kind of a little bit more high level basic stuff. But if you are wanting to use climate data, there's a lot of lessons that I've learned, kind of best practices, pitfalls to avoid. So this section is actually just running through some of the more practical aspects of using climate data because I want people to use it responsibly. Right. So if you're going to use climate data, understand what the data format is. Generally speaking, other than station data, you're going to be working with big data. If you're using climate data, it's big. I want to say it's chunky. It comes in like cubes. One of the most common formats is something called NetCDF format. So this is a self-describing and machine-independent data format that's been designed to work with this kind of cube data. So it's an array of data. So if you just look at the illustration at the bottom, so I want to say you've got a cube of temperature data. That cube is made up of, grid cells of latitude, grid cells of longitude. So if you think of a data set over Africa, the latitude, longitude, latitude and longitude, but it's a time series as well. So the other dimension is time. So the data is stored in binary in this cube, but it's associated with a lot of very well-defined metadata. So that's what I mean by self-describing. The data file has metadata associated with it. And if you just look on the right-hand side, I've just pulled out the metadata for this happens to be a file of air temperature, air surface temperature. It happens to be 1 hourly data over the full year of 2024. This happens to come from that Era 5 reanalysis product. So the data, as I said, it's got 3 dimensions. So the first dimension, in this case, they've listed as time. So this is number of time steps. So this is a year's worth of hourly data. So it happens to have 878,784 time steps. But then it also has 1,400 longitudes and 721 latitudes. This happens to be a global data set. So there are 1,400 grid points around. Okay. What it also provides information for is kind of list these as variables. So, time, latitude, and longitude are listed as variables. So it's got this like standard name. It also has its units. So in this case, they've used the units as for time as seconds since 1970. And they've specified what calendar. This might not make sense to many of you, but this data format is also used for climate projections. And some of the climate models actually use different calendars. They use a simplified calendar. Some of them ignore the leap year, the extra day in leap years. They just have a 365-day calendar year. And there's actually a couple that also make it even more simple, and they just have 12 months. Each month has 30 days. So that's specified in the metadata. It kind of, in a similar way, it says that longitudes is on the x-axis, latitudes on the y-axis, and then it describes what variable that is included in this. So TAS just happens to be temperature at the surface, or 2-meter temperature. As I said, we've got a very strict controlled vocabulary. We conform to some metadata standards. I never realized how well standardized our data was until I started working with health data. If you're working with climate data, you will realize how much time and effort has gone into standardizing everything. So for instance, this data set, the long name is 2-meter temperature. The units is in K, which is for Kelvin. It will tell you what is the missing value. So you don't have to, mess around with that. It will specify exactly what the missing values are. So I said this data is cubed. Sometimes they actually have 4th dimensions or 5th dimensions. So for instance, if you're looking at air temperature all the way up through the atmosphere, you would have a 4th dimension, which is the altitude up into the atmosphere. You'll have levels. This data set is just a surface data set. And so it says type of level happens to be surface. It also tells you that this data is an instantaneous value. It's telling you what is the temperature at midnight. The other data sets, which will be accumulative. So for instance, rainfall is often provided as an accumulative value over an hour, how much rainfall has fallen within that time period. So it's always important to go in and take a look and make sure that you understand what type of data this is. Then it just kind of, sorry, I think I didn't need to include the other things there. But so you have a very good understanding of the data because it's got a very standardized, very well-described metadata. Machine independent. So this just means that it doesn't matter. This kind of, you can work with this data on a Linux machine, a Windows machine. You can work with it in Python and in kind of R. It's very portable. Right. Next thing I want to bring up is, again, because this data is chunky, you can't just throw it into Excel or kind of just analyze it with kind of everyday tools. And so it's best to actually use the tools that have been developed for this type of data. So there are some resources out there that can list, these are the tools that you can use for coding language. You've got this. I will also put this in the link. I'll put this in the resources at the end. So it gives you a suggestion of, these are the coding language tools, data access platforms, processing tools. Don't worry about the evaluation benchmarking. That's for climate change data, analysis tools, Python packages, command line operators, and others. So interestingly enough, some of the command line operators are incredibly powerful. There's something called CDO, climate data operators. Within one line, I can do a whole lot of processing. I can take a whole lot of files. I can stitch them together, time files. I can put them together. I can convert the units. I can extract an area, a region. I can calculate anomalies, and I can do that kind of in one line on the command line. So some of these have been designed specifically for this data. And if you try and do these kind of things in, say, R, it's going to take a lot of time, and I don't know, maybe your machine might fall over trying to process it. So just be aware that it's probably worthwhile taking a bit of time and effort into using the correct or the most appropriate tools for climate data. Right. The next thing I want to focus in on is you really need to understand what the variables represent, how they were calculated, and what are the nuances of the different data sets. So I've actually just pulled this screenshot from, again, the Era 5 Explorer. So this is Era 5 data. And when you go onto their site, they actually give you a little bit of information about the data. And so what they say, so for temperature, they say it refers to 2-meter temperature from Era 5 reanalysis, which represents the air temperature at 2 meters above the surface. Over land, near surface temperature observations from weather stations are combined with that weather forecast model to improve accuracy. Just note that this is Era 5. It is the average temperature over a grid cell. Right. Then when you actually read up about what is the Era 5's, the rainfall or precipitation, what does it refer to? So this is total precipitation from Era 5. So precipitation is not the same thing as rainfall. Precipitation includes other forms. So it's snow, it's sleet, it's hail, not probably very kind of important for most of Africa, but just understand that precipitation encompasses more than just rainfall. But this is the key thing. In Era 5, they don't use precipitation observations to adjust the model. So this is a modeled output. So the data reflects the model's best estimate based on the representation of the physical processes. Okay. It's not adjusted, it's not improved using station observations. It still is influenced by other observations. So satellite measurements, for instance, humidity is very important, but no rainfall observations are included. Another thing to note is that rainfall, like tropical rainfall, convective rainfall, often it's quite contained. It's quite small scale rainfall. And these models can't account for these small scale processes. So thunderstorms, it can't represent that. And so these are parameterized, or they kind of, how would you describe parameterization? They're kind of fudged. It's a simplified kind of equation rather than being fully described in the physics. So what this means is for temperature, the skill of Era 5 might be better than the skill of precipitation. So sometimes, don't just grab one data set and assume it is going to be, as skillful. One variable is as skillful as another variable just because it came from one data set. Also, be aware that Era 5 is less skillful in the far, so Era 5 starts in 1940, but as I said, satellite data only comes in like 1980s. So there's a period then where there's less information, less observations going into the model. So especially if you're in a data scarce area, you're not having any observations in that reanalysis. So generally speaking, the skill of Era 5 is probably better in areas where there are more stations and also in the more recent past where we have satellite data. I also want to just kind of highlight that don't treat all climate data as interchangeable. In my mind, station observations are really the only kind of data observations. The rest are products. So for instance, if I'm trying to represent this in this little graph, so if you have a grid cell value, if you look at a grid cell of Era 5, you'll have a distribution of temperature values. I just pretended that maybe the mean is 20 degrees and it ranges between 20 and 30 degrees. Generally speaking, because it's an area average, it's going to have a smoothed distribution. But if you look at a point resolution, or actually if you look at a higher resolution, your distribution might look far more like the blue curve. Skinnier peak, maybe it's shifted, maybe it's a little bit warmer, and its tails might be longer. So depending on what you're wanting to use the data for, understanding these differences is important. If you're working with absolute thresholds, maybe your malaria, in this area with this mosquito species, we need, the optimal temperatures are between, 26 and 30 degrees. If you know that and you're working off an absolute thresholds, then these differences could be important. Or if you're really interested in the tails of your distribution, your extreme heat or extreme colds, knowing that the distributions are different can be important. So as I said, understand that a lot of these gridded products, it's an area average or area average estimate, which is, don't confuse that with point measurements. Another thing to be aware of is sometimes people assume that they know what the variable is, but they may be mistaken. So PR, we generally just refer to it as precipitation, but it's actually precipitation rate. And when you go into the metadata, you see that the units are kilograms per meter squared per second, which is confusing. This is equivalent to actually millimeters per second. So one of the first things that you get used to doing is you convert everything by multiplying it by 86400. So basically the number of seconds in a day, so that you then have your data in millimeters per day. So just be aware of these kind of nuances. Temperature is almost always going to be in Kelvin. You're going to have to do the conversion as well. Otherwise, you're going to, yeah, the temperatures are all wrong. Again, this issue of just be careful. It sounds pretty similar. So satellites will provide you with something called land surface temperature. This is not the same thing as air temperature. It's not the same as kind of 2-meter air temperature. It's literally that, the satellite is observing from above what the temperature is of the surface it encounters. That could be the top of a tree, and that could be a grassy field, or that could be that, black road. And if you've ever run barefoot across a tarred road, you'll know that the temperature is much higher than the air temperature. So just be aware, there are times when land surface temperature can be used and is appropriate to be used. But there are times when, it really is not the appropriate variable to use. So again, this really comes down to read the metadata and understand and read through the guidance to know what you're working with. Okay, so great. You've decided we're going to grab this data. Fantastic. But please, whatever you do, don't just use it as is. Open it up. Do a spatial plot. Do a time series. Plot the time series. You'll be amazed at how accurate your eye is at spotting problems. It's one of the quickest, easiest ways of evaluating the kind of the errors and the skills and sanity checking your data. And a lot of the time people don't do it. I've just provided 2 little examples. So the top example just happens to be a daily time series. This comes from a weather station. It's a time series of daily maximum temperature. It's for a place called Skakuza in South Africa. This is a fantastic record, actually. It's quite a long record and no gaps until you hit 2000, I think it is. And clearly the weather station I'm almost certain this was a manual weather station, and they decommissioned it. Then in the more recent past, they realized, hang on, we need data. And so they've kind of tacked on data. This comes from CSID. Sometimes this might be fine. That data might be good enough to be used. But if you hadn't plotted it, you wouldn't have seen that firstly, there's this, this big gap. And secondly, that, the CSID data, the later period, I would say there's a bit of a step jump. I'm not sure I would want to use that data. I would want to just use the data up till 2000. Okay. The bottom graph is showing a time series for Bulawayo. So this comes from Crew. So this is a gridded product. This happens to be monthly data. And what they do is they utilize surrounding stations. So they use up to 8 weather stations around it to calculate the value for each grid cell. So you can see it's a rainfall record. And the orange dot and line show the number of weather stations that were used to calculate this time series for the grid cell over Bulawayo. So you can see from kind of 1900 until I think you get to 2013, 2012. It's great. They had the maximum number of weather stations needed to calculate the data. But then the number of stations drops off quite significantly. At times there's one month where you kind of have generally six weather stations supplying data to calculate this value for this grid cell. But you can see at times there's, 1, 2, or 3 stations that are used. And actually, there are even times when no station records are being used. So in this case, what you do if you don't have any stations, they will just put in the long-term climatology for that month. So this is, this kind of metadata is really important to look at this kind of how much you trust the data, what is the skill. And actually, if I just eyeball it, I kind of think, it doesn't seem like the later period has as many extreme rainfall events. Is that true? Or is that just because it's not being able to properly interpolate from enough weather stations? So again, don't just grab the data, grab the metadata, grab any guidance documentation that you can. Okay, I think this is something that, sorry.
Lisa, sorry for interjecting. I guess
Yeah.
we are out of the time for the climate literacy.
I've got 2 more slides.
Yeah.
Quick.
Okay.
Cool. Okay, so something that I think you will be doing a lot. Either you're going to be pulling a grid cell value, or you're going to be aggregating. You will be aggregating probably over time and also over space. So if you're aggregating over time, there's just a couple of nuances that you should keep in mind. Sometimes, and this all comes down to what other data you're working with. So if your data is for a specific time of year or time of day, make sure that you're taking the climate data for that time of day or time of year. So for instance, if your mosquito surveillance data that you have, is only for the summer, don't associate that mosquito surveillance data with the, annual average data for climate. Associate it with the average, the climate, the time series aggregated over, for instance, the summer period, because that's when, your other data set is for. Also, there may be a tendency, I've only got 3 years of, again, sorry, I'm just going to use mosquito surveillance data. I've got 3 years of mosquito surveillance data, so I just need 3 years of climate data. I would say you need to have more data because you need to know whether or not those, if you're building, if you're training your model on that, you need to know whether or not those 3 years were hotter than average or were they kind of colder than average. Were they representative of, the general climate kind of over a longer time period? So just be aware, generally speaking, grab more climate data than you think you need so that you can then look at statistics. This is especially true if you're looking at extremes, because your number of extremes that you're going to find, the sample size is smaller. And then another thing, especially if you're working, I want to say in Southern Africa, the normal calendar year doesn't always make sense. If you're looking at rainfall, we have a summer rainfall over most of the region, and that straddles the year boundary. So maybe if you're doing a annual average, you're actually wanting to aggregate from July to June, because then you capture one rainfall season in one time step instead of having it split across 2. Then if you're going to be aggregating in space, so maybe you're going to be aggregating to kind of a box over your region, or maybe you're actually going to be aggregating to a polygon, a shapefile of your, say, district. What do you do with those grid cells that partially overlap? Do you make the selection of if any part of a grid cell is in, it's in, or maybe you're a little bit more sophisticated and downweight the grid cell depending on what percentage of area is included. Also, it's probably a good idea to mask out any water bodies. The temperature of the ocean and lakes is going to be different to the temperature over land. So be a little bit more nuanced in how you cut out or aggregate to your area of interest. This is also an interesting thing. So sometimes, yes, you might just want the mean. So this is where the time aggregate and spatial aggregation comes together. Maybe you just want the long-term mean for your area. But there may be other times where you actually are more interested in kind of some of the statistics of the climate. Maybe you want to look at the number of rainfall days or rainfall events, or the number of days above a threshold, a number of days when the temperature is within a suitable range, etc. So it's worthwhile thinking through some of these nuances before you actually just pull out the data and plug it into your models. Then this is the final slide. I'm not sure if everybody understands the difference between regridding, interpolation, and downscaling. People working in kind of the geospatial world, this is like something that is very easy to do. If you go on Google Earth Engine, you can do this very easily. But you need to be careful of, firstly, what methods you use. But more importantly, it is really important to understand that regridding, interpolation, you can go to a higher resolution, you can change the scale, but no added information. You do not get more information out of this higher resolution data. It looks nice, but there's no added information. The skill level is at that native coarse resolution. This is different to downscaling. When kind of new information is added, you are getting, there is actually value in the differences that you see in the high resolution product. The methods are a little bit more complex. Some people will be actually running a regional climate model inside the global model. You get quantile mapping. And actually, there's a lot of work now looking at the different machine learning approaches to downscale. But yeah, just be aware of what the differences of kind of regridding, interpolation, and downscaling are. And yeah, check whether or not is it even appropriate to interpolate your data. And that's where I'm going to leave it. Cool. So
Right.
I think the idea is now to have a break, but I'll leave it to you.
Yeah. Okay. Thank you so much, Lisa, for that wonderful introduction to
Cool.
climate literacy. So I guess we'll be going for a 10-minute short break. And I encourage you to just stretch your leg and also grab a cup of coffee for that 10-minute break. We'll be back for the practical section. See you in 10 minutes time.
Cheers, everyone. Cool, thank you. Yeah, we're going to go straight into the breakout sessions. So this is a bit of practical work. I don't want to take too long to kind of waste more time. So what I'm asking each group to do is to go into Era Explorer. So this the Climate Data Store, Copernicus Climate Data Store. It's a pretty massive what would you call it? It's a data visualization, it's a data access, and it's also a data guidance kind of platform. And one of the visualization tools they've got is called Era Explorer. So we're just going to go into this Explorer just to look at data. So what I'm asking is each group just to pick 2 locations. First location, can you try and pick one that is suitable for a specific climate sensitive infectious disease, and then another location that has a very different climate. And what I'm asking is that each group just look at the graphs and see if you can interpret them, and then link these insights to CSID suitability. So if I break that into kind of questions, look at it and see what is the seasonality of rainfall and temperature and humidity, and how do they differ between locations? For instance, when is the warmest time of year? When is the coolest time of year? Do they have strong variation, diurnal variation, strong seasonal variation? When is the start? When is the end of the rainfall seasons? Things like that. And then for the location where, it is suitable for the disease, look at, the suitability and how the different variables line up. So for instance, how many months is the temperature suitable? And are those months also, is there sufficient rainfall and humidity during those months to get an idea of this? Remember, this is reanalysis product. This is not truth, but this is just to play with data. And then there's a couple of other graphs that are time series graphs, and just take a look at it. Look at it and see how much variability is there on, kind of annual, so interannual variability. Are there any decadal variability, and is there any trend? So that's the idea. We have people within each groups to facilitate. So I think we can shift into that.
And just a quick comment that we have at least one breakout room for French speakers. So if you prefer to be in a breakout room with French facilitation, please either raise your hand or put a comment in the chat, and then we will take you to that breakout room. And in the meantime, Ricky, are we ready to open the breakout rooms?
Yes, we are ready. I can just hit the button, but if there are people raising hands or commenting, I need your help, Irene, because to assign people. So it's just
Yes.
I have a different screen at the moment in front of me.
Yes, please open them.
Okay.
Okay, they are open. So we will be back in around 20 minutes. Is that all right, Lisa?
Yeah, and can I ask, if your bandwidth allows, could you put your cameras on? This is too big, but when we're in the breakout rooms, it's nice to be able to talk to faces rather than to names.
Okay, I'm gonna pause the recording for the activity. Pass it over. Hi. Okay, so for the recording. Hi, everyone. Everyone is back from the activity. I'm gonna pass it to Daniel to maybe surface some of the questions. I know we have one in the shared document, and then we can do the closing.
Okay, all right. Hi everyone. I hope we do enjoy interacting during the breakout section. I guess we do have a quick questions for Lisa. I think and then from there we would hand over to Sam. So there's a question in the Google Doc saying, do you think we should calibrate AR5 land data before putting it into the model?
Yes. So if you are fortunate enough to have weather stations in your region, it's a really good idea to look at, what the biases are. Also, it's a good idea to look at literature. So ERA5 has been used a lot. So other people have also done analysis. They've already, looked at it and see here it has a cool bias, here it has a warm bias. Also, just remember, maybe if you're using rainfall, maybe Era 5 isn't the most suitable data set to use. It's really easy to use because it's there. People have done a lot of work in making it accessible. But for rainfall, if that is a key variable, maybe look at some of the other products that are available. And as I said before, I'm going to be providing, I'll send it through via Angela or whoever's going to be corresponding with you. I'll send through a document just listing some of the resources, some of the data sets, some of the places you can go to learn more.
All right. Thank you so much, Lisa. So I guess we would hand over to Sam to close the session and then tell us more about the next step moving forward.
Sorry, Daniel, there's one more person typing in a question. I wonder if we have time for that.
Okay.
And maybe they could even speak it.
All right. So yeah, okay, yeah. So these are another questions. Saying what's your opinion on the use of climate data only to predict future spread of disease due to climate change, particularly mosquito-borne disease? Yeah.
Yeah, so that is I probably should have been a little bit more explicit about this. I had to cut this down quite a lot. And so I only focused on kind of historical kind of climate data. There's a huge amount of other data, seasonal forecast, climate projections that are out there. And if you're wanting to look at how the diseases are going to kind of spread into new areas, you're going to need to use those kind of data, types of data. The guidance on using those kind of data, I would need another 5 hours to cover. So yes, you can use climate change projections to look at this, but do some research before just doing it. Or maybe include a climate scientist in your group, so that you guys can do it together.
To gauge interest, I wonder, I just put a question in the chat. Maybe people can respond under it, but would you be interested in having a future session about this? Let us know if this sounds of interest, because like Lisa was saying, there's just so much to cover. So we had to ask her to really pare it down into something small, but it'd be great to know if this is something that you all would be interested in.
And then I have to talk about ensemble space, woohoo, and scenarios. Great fun.
Yeah. So I guess I'll hand over to Sam so that you could wrap up and then tell us more about the next thing, like the feedback survey and the likes.
Yeah, sadly, all good things come to an end. It's time to close this exciting session with Lisa. Yes, we're going to have future sessions, and so it will be helpful if you could give us some feedback. And so we're going to share a survey to all attendees to give us some feedback based on the experience we've had today, what you think we could improve, etc. That will be really appreciated. Thank you in advance. And also there will be certificates of participation. So look out for that, especially if you filled the feedback survey. Yeah, the feedback form has been shared. It's already in the chat. But I'm sure we would also send it out later in case you still don't have it. Yeah, and you can still be a member of CSID network if you have it in mind. In January, we are opening up to public membership. There are several ways you can join and support and be an active member. You could be a core member, and you could join as a partner organization or as an individual participating in member-only activities, or you could support our organization of things like events and activities. So once again, I would like to thank everyone for making it to our very first session. You've helped make it a success. Yeah, we should all clap for ourselves. Yeah, and thank you, Lisa. Thank you, everyone. Thank you, Training and Education Committee. Thank you, CSID, Angela, and yeah,
And huge
everyone in
thanks
the
to Sam for your help, Daniel, Bado, Irene, and also Lisa's colleagues. I know you also came to support Lisa.
yeah,
I think it really was a huge effort from so many people. So just a huge thank you to each and every one of you.
very
And everyone
huge.
for coming.
Yeah, thank you for coming. These are very quick, useful links to learn more about CSID.net. If you have questions, you can send it to operations@csidnet.org. And then please don't forget to subscribe to our newsletter. It's a sure way to hear about what's happening in the network and future sessions like this. You can quickly scan the QR code or use the link if you want to. And so till we meet again for our next session, I'll say bye-bye for now and have a nice day, everyone.
Thanks, everyone.
Thank you.
Au revoir.
Bye-bye.
Kwaheri.
Au revoir. Ciao, ciao.
Ciao.
Ciao,
Asante.
ciao. Bye-bye. Wow.
Hopunka.